Welcome students. We want to discuss about changing variables in multiple integral. Let's start with 1D example. In this case, suppose you have the following integral. You want to evaluate 0 to 1 x times square root of 1 plus x squared dx. Now we know that the inside integrand does not has an elementary antiderivative. So one way to go about this is the following. Let x square 1 plus x squared be u, and then we need to change dx as well. So we get 2x dx equals to du, and in that case we get x dx equals to du over 2, and then we substitute in, we get integral becomes 1 plus x squared is u, we get du by 2, and the limits of integration are now when x is 0, we get u is square root of 1 plus x square, which is 1 plus x square, which is u. So u is 1 then, and when x is 1, this means your u is 2 square root of, u is 2. So you get 1 to 2. So this is what happens in 1D integral. So you do a transformation here, and if I want to write it in general form, you are essentially, what you're doing is you are, if you have integral a to b fx dx, and you're doing the transformation, so the new limits is alpha to beta, where alpha is u inverse of a, beta is u inverse of b. Then we have f of x of u, and then because x of u is, you're writing x in terms of u multiplied by x prime of u du. Okay, so you are choosing x equals to x of u. So this is what you're doing in function of one variable. All right, so now if you want to generalize this case, now let's look at the second problem, integral of e to the power x squared plus y squared dA, where e is enclosed by the disk in the first quadrant. All right, so E is this disk essentially in the first quadrant. So how does your region looks like? Your region looks like it's a part of circle in the first quadrant. So this is your region D. Now note that you cannot evaluate it in, evaluating this in Cartesian coordinate is not possible, right? So we'll like to do some transformations here. And we have already seen that the transformation which will work, because it's a disk, x equals to r cos theta. We had y equals to r sine theta. So then your integral becomes integral of e to the power. So r, and now instead of dA, we will have r dr, r dr d theta. So your dA changes to r dr d theta, right? And then if you look at the geometry, now in this case, this can be seen as a polar rectangle. So I'm calling this region was called E. So let's keep that. So this is E, and E in polar is given by, so your R goes from 0 to 3, and theta goes from 0 to, so R theta, R goes from this, and theta goes from 0 to pi over 2. So your region E has transformed into, if you look in r theta coordinate, it has transformed into a rectangle, right? A rectangle with theta as pi by 2 and r as 3. So this is your transformation. You are now integrating over this r theta, so this region over the polar coordinate. So let me call this as, if this is E, let's call this transformation to be T, then this is integrating over T of E. Okay. So we get this can be, well, I mean, let's rewrite the integral, so which we can say that it's easy to compute then. So 0 to pi by 2 e to the r dr d theta, and then we had so I'm choosing, let me choose now, since it's a rectangle, I can choose any order. So I have d theta dr, and I have 0 to 3. So there are two things to observe here. One, that your area element is replaced by r dr d theta. Now, why is that a case? So when you are basically looking at the, when you're looking at the rectangular, so when you're looking at the piece of disk, if this was, if this part was your r, if this is your r here, and this part is dr, if this is d theta, then this side is going to be r d theta, and when you get multiply it out, you get dA equals to r dr d theta. So your area element dA has changed to r dr d theta. So this is using the geometry of it, right? The geometry of the area element you are choosing. So you're using small polar rectangles to find out the whole integral. Now, what if instead of this polar transformation, x equals to r cos theta, y equals to r sine theta, I have a general transformation, x equals to some function, say g of u v, and y equals to h of uv. Then if I do such a transformation, how will my integral transform? Okay, so for that, let me introduce new object here, Jacobian of transformation. So if x is given by g of u comma v, y is given by h of u comma v, then the Jacobian of x, y respect to uv, this can be called j, is partial derivative of x with respect to u, partial derivative of x with respect to v, and partial derivative of y with respect to u, and partial derivative of y with respect to v. And it's a determinant of this object. So determinant is this guy multiplied by this guy minus this guy multiplied by the other one. So you multiply the diagonal ones and subtract them. We have already seen this when we were doing the cross product. So this is a Jacobian, and the idea is that the area element is related to the Jacobian in the following way. So the new area is going to be dou xy dou r uv delta u delta v. So let's revisit this in terms of polar coordinate again, in terms of Jacobian, and see what do we get. So in this case, we have, so in our case, new scenario, we have x equals to r cos theta, we have y equals to r sine theta. And we are having this transformation. So x is written in terms of g r theta, if you want to write like that. And then this can be written as h of r theta. So now let's compute the Jacobian now. In this case, the Jacobian is going to be partial derivative of x with respect to r, partial derivative of y with respect to r, partial derivative of x with respect to theta, and partial derivative of y with respect to theta. Let's compute this. So this partial derivative of x with respect to r is going to be cosine theta. Partial derivative of y with respect to r is going to be sine theta. Then we have partial derivative of x with respect to theta is going to be minus r sine theta. Partial derivative of y with respect to theta is going to be r cos theta. So if you cross it out, you get r cos square theta plus r sine square theta. That is going to be r. So this result tells us that the area element dA, yeah, this is roughly like dA, is going to be j times dr d theta. And what is your j? J turned out to be r. So we get dA equals to r dr d theta. So you see how this Jacobian technique helps us to generalize. So here I'm just doing an example. It can be done for any transformation really. Any transformation T will come to that, what kind of property this transformation needs. Of course, this transformation has to be, for example, 1, differentiable and so on and so forth. So we'll come to that in a minute. So that is the question we are wanting to ask here now. What kind of transformations are okay, right? I mean, so the transformations which are okay are the following. So let x be function of u and v, y be function of u and v. So we are transforming x and y in terms of new coordinate system u and v. Okay. Now suppose we are writing it in a slightly different format. So suppose your x, y are transformations of u and v. That means x and y are, in your case here, in the polar case, we had x, y equals to t of r theta, and that is same as t1 of r theta, t2 of r theta, and the first one was r cos theta, r sine theta. So here's the transformation. So you have x is a function. So if you take t of u1 v1, you have x1 y1. And then the inverse function, t inverse, will take x1 y1 back to u1 v1. Yeah. So to define this inverse, we need to have t to be a 1 1 function. Okay. So we are only considering 1 1 function. What are 1 1 functions? 1 1 functions are functions which take two different elements. If you take u1 v1 and u2 v2, if these two elements are different, then the images are different. Or if you look at it from contrapositive, that if t of u1 v1 equals to t of u2 v2, that can only happen when u1 v1 equals to u2 v2. Okay. So in this case, if you have such a map, if you call this as t, then u1 v1 is called pre-image of transformation, and xy is called image of the point, right? So image of u1 v1 is x1 y1, and pre-image of x1 y1 is u1 v1. So let's call S to be pre-image set. So S is a pre-image set because pre-image means going back here under T, and R is the image set. So we have R equals to T of S. So again, what kind of transformations we are allowing? We are allowing the transformations which are 1 1, and they have to be differentiable as well, but that is not discussion much. We'll come to that in a moment. So now, given R and T, question is, how do we find out S? Okay. So suppose D is a region bounded by 1 over x, y equals to 2 over x, y equals to x squared, and y equals to 3x squared in the first quadrant. Let T be UV such that T of UV be xy, where U is given by, the map is given by xy, U equals to xy, V equals to y over x squared. So note that T is not a linear transformation, all right? So that is something, I mean, T generally, if you have done linear algebra, we discuss T as a linear transformation, but this is just a transformation, all right? Yeah. We need actually this transformation to be continuous and differentiable, such they are called C1 transformation, but that's not our concern at the moment. So let's find out. So let's first draw this region. So how does this region looks like? So we have 1 over x. So we have 1 over x, which is the following sort. We have 2 over x. And x is 1, this is 2. We have x squared, which is goes like this. And we have x cubed, 2x squared, sorry, 3x squared, which will be, okay. So this is our region D. Okay, so let's color this up. So this guy is, so this is 3x squared. This one is x squared. This one is 2 by x. This is 1 by x. So basically, so this is your region D. Now let's see, what does it transforms to? So first of all, if you have u and v, so u is xy. So from the first one, you can see that u equals to 1 over x. So now we want to draw the transformation of this. Now, how do we find the transformation? So the main method is actually to find the image of the boundary. So we'll see, where does this image, this one goes to, where this goes to, where this goes to, where this goes to. So we have 4 boundaries, and we'll see where do they go to. So we have u equals to xy. So first one, y equals to 1 over x, gives me xy equals to 1. Similarly, the second one, y equals to 2 over x, gives me xy equals to 2. So if you look at this, this is same as u though, right? So u equals to 1, and this is u equals to 2. Yeah, that's already looking nice, because it's at least on u, it's a u equals to 1 and u equals to 2 are straight lines. Now similarly, we have v equals to y over x squared. So now v equals to y over x squared. So we have, so if you look at this one, y equals to x squared gives y by x squared equals to 1. That implies this boundary is getting transformed to v equals to 1. And here we have y equals to 3x squared gives me y by x squared equals to 3, which gives me v equals to 3. So this region D, so if T was a transformation from uv to xy, this is, let's use a different color pen. So suppose this was u, this was v, we have u equals to 1, to u equals to 2, v equals to 1 to v equals to 2. So, and this region is T inverse of D. Okay, so let's just color this up and then write outside. So this region is T inverse of, this region is T inverse of D. Okay. So you see now your region D has transformed into a nice um, rectangle. So if we have to integrate, we have now, instead of having these limits of integration, we have better looking limits of integration. So we'll see that, we'll explore that in a moment. So this theorem tells us how the change of variables in the double integral works. So suppose T is C1 region, C1 transformation. So what is a C1 transformation? So C1 transformation is basically transformations is continuously differentiable and has an inverse. Okay, so this is what the C1 transformation is, whose Jacobian is non-zero. And the map S from UW plane, it maps S from UW plane onto region R in XY plane. Suppose F is continuous on R, and R and S are only type 1 or type 2 regions, right? Or X first or Y first region, right? X first or Y first region. Suppose also T is 1, 1, except at boundary, then we get that double integral of R, f of x by dA is, instead of x, you substitute uv, right? X is a function of uv, so write that. Y is a function of uv. The important part here is, so we have du by du dv, but the important part is multiplication by this Jacobian, right? And this gives you the transformed integral. Okay. So again, so computing this Jacobian becomes interesting now, right? So we have already seen this in terms of, so in cylindrical coordinates and so in polar coordinates, we have already seen dA equals to R dr d theta. In cylindrical coordinates, we should be able to see that if you do the transformations, you will get R dr d theta dz. And for cylinder, so this is for cylindrical. And you should be able to see the similar one for the spherical. So for spherical, we'll derive in a moment, all right? We'll show that for spherical, this is the same. All right, so this is the idea behind change of the coordinates or change or the transformations, changing variables in the multiple integral. Question, why do we need to do this? Well, we need to do this so that the geometry, so that we can align the geometry and get a simpler geometry. For example, from so suppose this is a circle of radius 3 to theta r. In this case, we have pi by 2 to 3, right? So we have a simpler geometry which we can use to integrate. And sometimes it simplifies the integrand for the antiderivative. I mean, particularly here, right? You could see that in this example, it would have been really difficult to compute the integral, but if we tried to do it directly, but if once you change the coordinate system, you could have left the substitute. Here you can do the by parts and work it out. Okay. All right, so let's explore this idea with some examples. So suppose I'm given to evaluate e to the power xy divided by x minus y dA, where R is a trapezoid whose vertices are 1, 0, 2, 0, 0 minus 2, 0 minus 1. So what do we have? We have we have 1 0. So if you draw this trapezoid, we have 1 0, which is x is 1, y is 0. Then we have 2 0. Then we have 0 minus 2. And then we have 0 minus 1. So this is your boundary of the region, and R is this region here. And you want to compute this integral on that. Now, the region R is simple, but the integrand is complicated, right? It would be hard to integrate this guy. So what we'll do is we will transform now everything to UV plane. So what kind of transformation makes sense? So we'll simplify these guys up. So let's say, let's use the transformation x plus y equals to u, and x minus y equals to v. Okay, so now we do that transformation. So the integrand becomes, so the integrand, let me write down the integrand here. It will become u over v, right? So now we need to, of course, multiply by the Jacobian. What Jacobian are we multiplying? We are multiplying by xy uv du dv. Even the absolute value of this Jacobian. So we need to find out. We need to find out. So for computing that, we need partial derivative of x with respect to u, and partial derivative of y with respect to u, and so on and so forth. So how do we compute that? Well, one way is to compute it implicitly, or otherwise you can write it down. X equals to, if you add both of them together, you get 2x equals to u plus v. And if you subtract them, you get 2y equals to u minus v. So this gives me x equals to half u plus v, y equals to half u minus v. So therefore, Jacobian J is going to be partial derivative of this with respect to x. So let me just write down with respect to u. Then we have y with respect to u. Then we have x with respect to v. And we have y with respect to v. And in that case, we get partial derivative of x with respect to u is going to be half again. Then we get partial derivative of x with respect to v, half, partial derivative of this with respect to v, minus 1 over half. And then when we take the integral, when we take the multiplied out, we get minus 1 by 2. So we got that so we got this to be half. All right. And then we need to take absolute value of that, right? So, but now we also need to find out the bounds on our region. Okay, so let's try to do that. So let's find out what are the bounds on my u and v. So again, we need to basically deal with the boundaries. So the way to get the new region is to look at the boundary of new region S by looking at the boundary of old region R. So let's make an equation out of these. So if you use the intercept form, you will get for this line, the equation is going to be x over 2 plus y over 2 minus 2 equals to 1. If you basically multiply it throughout by 2, you will get x minus y equals to 2. Same thing can be done here. You will get x minus y equals to 1. In this part, you will have x equals to, you will have x, x equals to 0, and here you will have y equals to 0, right? So we have, in this part, we have x going from 0, and we have y equals to 0. So now let's see how does that transforms. So let's see. So x minus y equals to 2. So this region, if I want to write it in, so this can be written as u going from uv. So we have written, this is our u, right? So we can write v directly between 1 and 2. Now, what is x plus 1, x plus y equals to 2? So we have this region now. We need to write down for what is the thing for y. So we get, in that case, so here x equals to 0 would give me u plus v equals to 0, and y equals to 0 will give me u minus v equals to 0. So if you notice, your you are between your, you have already chosen for v, and your u is between minus v to v. So then your region of integration becomes, so in this case, so we have, now we can write it down as, this is our region, and the integration becomes 1 to 2 for v, and u is from minus v to v. So let's understand this once again. So the idea is, how do we go about it? You have these points, and you see where these points x and y are going. You write down what is u and v. Say, for example, what is 1, 0, 2, 0, 0 minus 2, 0 minus 1, go under. So they correspond to what in the UV. So when x is 0, 1, 0, you get u is x plus 1. So we get x plus y. So this will be 1, 1, as we got here. We have, so we got it here. When x is 2, 0, you get again x plus y, 2, x minus y, you get again 2, 2. So you got this point. Then 0 minus 2. If you take 0 minus 2, you get x plus y is minus 2. And x minus y for v is going to be 2. So you go to this point here. Then you have 0 minus 1. When x is 0, you get x is 0, you get u is basically minus 1, v is 1. So step 1 is essentially, so this is your step 1, understanding new geometry. And also note linear maps, map lines to lines. So in that case, when I got these coordinates, I just joined them because I know that this is a linear map and they map to join, right? So after the first step, so this is step 1. So I should write that step 1. So understanding the new geometry is the step 1. And so we then map, we see that R gets mapped by from, so R is the image of S under T. All right. So now once we have S here, we can see that S goes from, so this is a step one. Now step two, we can basically, so we can have R basically, so S is, let me just finish the step one. So S can be written as UV, where your 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 V is basically between, U is between minus V to V, and then U is from this to 1 to 2. Okay, so this is how you write down your S. So step one. Step two is about computing the Jacobian. So we compute the Jacobian. Step three, write down the integrand. So integrand is now e to the power x plus y, which is u over v. Okay, and then step four is basically an integration plan, which is writing the integral down here, and we get minus 1 to 2 minus v to v e to the power u by v times d. What is first? We are doing dv du. Now, since we said that the integral is easy to compute, we should compute the integral as well. So what is the integration of? So we have du dv, right? So then integration with respect to u is e to the power u is e to the power u. So this is going to be e to the power u times v divided by 1 by v, which is multiplying by v. So minus v to v minus 1 to 2 dv. So then that is going to be integral minus 1 to 2. You put e to the power. So now we have, instead of u, we are going to put v. So we have, when you put u by v, so when you put v there, you get e to the power v by v, which is 1 times 1 minus e to the power minus 1 v dv. And then, of course, let's not forget this was half. So times half times half. And that turns out to be, if you integrate this, this will turn out to be 3 by 4 e minus e to the power minus 1. So this is the whole stuff. Okay. Now let's proceed and do the same problem here again. So we have y equals to 1 over x, u equals to 2 by x, y equals to x squared, 3 equals to y equals to 3 by x squared. So in this case, you recall, we already have done this finding the region. So our region turned out to be a rectangle. So step one is to understand the geometry. Step one. Okay, you took, again, I'm going to write it for the sake of completion, xy equals to u, and we wrote we wrote y, v equals to, we wrote v equals to y by x squared. V equals to by x squared, or that is same as saying, so xy equals to u and v equals to y by x squared. So we wrote, okay, so now we get geometry is, we got a rectangle. So your u is between 1 and 2, and your v turned out to be between. So if we divide on this side, we get v equals to, v is between 1 and 3. So we got u is between 1 and 2, and v is between 1 and 3. Okay, so this is what the region will look like as we got here. Yeah, so this was 1 and 3, this was 1 and 2. Okay, so that's first step. So we got the geometry on the way. Step 2 is, let's compute the Jacobian. So we want to compute J of, we want to compute J, which is partial derivative of this guy with respect to uv, that is x with respect to u, y with respect to u, x, y with respect to v, and x with respect to v. So now what is a, so we have here, we want to write x with respect to u. Now how do we go about that? Well, here we do not have x in terms of, we have to write x and y in terms of u and v. So either we do that or we can do it implicitly. So we'll try to do it in the following way. So in this case, we can write, so how do we get u and v in terms of x and y in terms of u and v? So we have, if we divide equation 1 by 2, you get u by v equals to xy divided by x over y over x square, which is going to be x cubed. So cube root of u by v equals to x. Therefore, y is going to be u by x, which is going to be u upon cube root of u over v. That is going to be cube root of v times second root of u. So now how does our Jacobian J looks like? So J is going to be partial derivative of x with respect to u. So that's going to be, you can keep, so you have cube root of, so derivative of cube root is 1 by 3 uv to the power minus 2 by 3 multiplied by derivative of the inside with respect to u, which is going to be 1 by v. In this case, we'll have with of y with respect to u can be written as dou y by dou u can be written as cube root of v times 1 by 2 root u. Then here we have dou y by dou v, which is going to be again 1 by 3 u by v to the power minus 2 by 3 times derivative of inside with respect to v. So it's going to be u times 1 by v square with a minus sign. And dou x by dou v is going to be, sorry, so the order should be y, sorry, x and y here. So this should have been This is correct. And then we have dou y by dou v, which is going to be 1 by 3 v to the power minus 2 by 3 times square root of. So now we need to compute this Jacobian.